Welcome back, Chem 1110 students. We are going to follow up on video 2 here and talk some more about the quantum theory and electronic structure of atoms. If you remember, we left off in video 2 with realizing that the Bohr atomic model only worked for hydrogen, which of course limited it a great deal since there's many more elements than hydrogen that are of interest. So we're going to look at a little background material about what was known about electrons at the time. And we start with the fact that we know that light moves as a wave, and people knew that because they saw rainbows. The white light from the sun was diffracted by raindrops into its various colors, just like a prism. And then Einstein in the early 1900s said, well, light can actually act as a particle as well as a wave. And this has been demonstrated to us by, things like solar calculators. Sunlight hits that solar panel, it knocks electrons off of the semiconductor in that solar panel, and that stream of electrons is an electric current. So therefore we know that light can act as both particles and wave. And so Louis de Broglie said, well, if light can behave both ways, maybe electrons can too. So we know electrons are particles, but maybe they can act like a wave. And that can be described by equations because at that time, in the early 1920s, mathematicians were doing a lot of work on equations that described wave motion. And so the one that sort of worked was a Schrodinger equation. And when you solve the Schrodinger equation, you get sort of a probability map of where the electrons reside, and it turns out that they're in something called an electron cloud, not an orbit. So Schrodinger's formula described both wave and particle characteristics of an electron. The wave behavior is described as a wave function, which has the symbol psi, which looks like a little pitchfork. And it defines a region where the electron is most likely to be. And so it looks like a fuzzy cloud where you can see that the electron density would be greater around the nucleus than very far away. It also specified, as did Bohr's atom, that there are specific electron or energy states that the electron can occupy. And when you solve this equation, which you will never have to do because it's very complex, the solutions describe where this electron probability is. And these are referred to as orbits, not atomic orbitals. And here's an example of one for a particular kind of electron. And you can see the electron density is in two, not really spheres, kind of teardrop-shaped areas along the z-axis. And we might actually call that a dumbbell shape. And so in solving Schrodinger's equation, you get these solutions, and we call them quantum numbers, and they describe this electron distribution. And they are the quantum numbers are necessary to describe the atomic orbitals, and there are three of them. The principal quantum number is n, designates the size. So that's just like the n being the number of rows in the periodic table. The angular momentum, which is given the letter L, describes the shape, and the magnetic quantum number describes the orientation. So in other words, whether it's along an x, y, or z axis. And so we're going to look at this a little more closely. Looking at that principal quantum number, which designates the size, excuse me, we realize that means larger values for n means there are larger orbitals, which is sort of something you might expect looking at the periodic table, because you're squeezing more and more electrons in as you go down the periodic table. Those allowed values for n are all integer numbers, and so they do equate to the row number in a periodic table. And it just so happens that n does correspond to the value of Bohr's model, which is why we still look at Bohr's model of the hydrogen atom, because there was a lot in that makes sense. Now, sometimes you have a collection of orbitals that all have the same n value. So these are for the elements that are all in that row, maybe the third row. And so these, where these electrons reside, are called a shell. So it's sort of like an energy shell. Looking at the angular momentum quantum number, which is L, it describes the shape of the orbital. And the value of L depends on the value of that principal quantum number. They're related to one another in that the L value is going to vary from 0 to n minus 1. So for instance, if n equals 2, we're talking about the second row of the periodic table, then L can only be 0 or 1. And here's a little chart that shows you the designations. At the top is the L. It kind of looks like a 1. It should be a script L. And so if it is 0, that means it's an s orbital. If it's a 1, it's a p, a d, and an f, and we'll discuss those more. And once again, if it has the same value of n and L, it's referred to as a subshell. Okay, now we're going to look at the magnetic quantum number. This describes the orientation, which way it's pointed in space, and the values that you can get for the magnetic quantum number depend on the value of L, that angular momentum quantum number, and it can go from minus L through 0 to positive L, and I'll give you some examples. So this is a nice chart. If n equals 1, L can only equal 0 because L is equal to n minus 1. If L is 0, then m sub L is 0. But if n is 2, so we're talking about the second row of the periodic table, L can be 0 or 1. And if it is 0, then m sub L is only a 0. But if L equals 1, then m sub L can be minus 1, 0, and plus 1. So you're probably asking yourself about now, why does this matter? Well, it describes a couple of things. It not only describes a periodic table, but it tells us not only where the electrons will be found, but how many orbitals are in the subshells. And so you can see in this chart in the lower left-hand corner, when n equals 1, then we have L equaling 0, and each of those n values has a situation where L equals 0. For the second row of the periodic table, L can equal 1, which means that m sub L can be minus 1, 0, or plus 1, like we talked about. Those are called p subshells, and I've got some pictures coming up of that. First off, we're going to look at this example, and it says, what are the possible values for the magnetic quantum number, so that's the m sub L, when the principal quantum number is 3 and the angular quantum number is 1? All right, so what we have to remember are the possible values of ml depending on the value of L. Doesn't depend on the value of n, because that could be several different things. So if n equals 3, then L, which is equal to n minus 1, can be 0, 1, or 2. We were told that L equals 1, therefore the possible values for m sub L are minus 1, 0, and plus 1. And I do realize it will take a little bit for you to remember all of this. All right, so there's another quantum number, and that's the electron spin quantum number. And this is important because there's only two possible directions something can spin, clockwise and counterclockwise. And these are given the magnetic or the electron spin quantum numbers that are plus 1/2 and minus 1/2. So they go in opposite directions. Here's a little picture. And the interesting thing is if you take a charged substance and you spin it like an electron, it creates a magnetic field. And so you can see with it spinning one direction, the magnetic field is such that the north is up, the south is down. You spin it the other direction and it flips that magnet. And what this allows is for electron pairing, because we know with magnets that the north and south poles are attracted to one another. Okay, so I'm going to summarize quantum numbers here, and then I think I will change and go on to another video. So the principal quantum number is n, and that gives you the size. The angular quantum number is L, and it gives you shape. And the magnetic M sub L gives you orientation. And you need all three of those to describe an atomic orbital. And we have a notation for that. And so it'd like be 2px. So your principal quantum number is 2. The angular momentum is 1, so it's a p orbital. And the M sub L tells you the direction. It tells you it's an X, so it would lie upon the X axis. And this is a picture of what that would look like. Let's see what I have on my next slide. Oh, and then of course the electron spin is not shown in that notation, but we do know that it tells you which way the electron is spinning.